Living Room Logic.
Welcome to Living Room Logic, a place for you to chill out and have a laugh with two scientists who know too much about very, very little.
This episode, we explore the tiniest things in the universe, how particle physicists just like to smash things together at incredible speeds, and why quantum physicists think the universe is tied together by cosmic shoelaces.
Create a parallel universe and follow the podcast on Spotify or Apple Podcasts. If you enjoy what you hear, maybe leave a review or tell a friend. Come find us on Instagram or Twitter or other social media that you both use and don't use at all. Sit back and enjoy, because none of this matters.
Okay, everyone, welcome to Living Room Logic, where two biologists who are giddy on alcohol, especially Andrew, who's Bailey's giddy right now.
Can you blame me?
No, not at all. In fact, I encourage it. And today, these two biologists are gonna, we're gonna try the insurmountable. We're gonna try and explain physics. And not just any physics, but some really difficult physics. Oh, we studied hard this week, everyone, okay? So you're gonna love this.
Oh, like for a final exam in a module you didn't go to the lectures for. That's how it felt.
Honestly, gotta give it to physicists. They are some smart dudes.
Yeah, legit. Anything like that, that was sweet. And we're going to need it. We're going to need plenty of those noises this episode.
Oh, we're going to need these.
I think physics is something that for the most of the time is just intuitive, right? It's you don't need to know that cycling harder makes you go faster, okay? That's an intuitive bit of physics, right? But when we talk about the classical physics, like what you're really thinking about, how do you calculate what goes faster at what rate, etc. You kind of go back to your man who saw an apple fall from a tree, Mr. Isaac Newton.
That dude with a wig.
They all had wigs back then if you were in the Royal Society. It was a rite of passage. But that he basically measured how quickly things would fall to the ground. He measured gravity, and he kind of used that to, do what was trendy at the time and go, oh, cool, we're all looking at planets. That's what all of us physicists are doing because, they're big and unexplained. Let's do it. And he made these equations that could kind of calculate everything that was going on at a solar scale. Okay, he would calculate how to use orbits. He was the creator of calculus, which has tormented so many students across the centuries since. And that's a lot of the foundation of physics. And anyone who takes a physics course or anyone who does physics in their end of school exams, they learn some mechanics. They learn some classical physics that Newton did. And that's, to be honest, that's easier because you can see them. Okay, you can look at it and you can see it. But when you say, okay, let's look at something smaller. So instead of a planet, you look at a rock. Okay, you can still see that. What if you cut the rock in half and then you cut the rock in half 1,000,000 times and then it's completely unobservable? It's much harder to come up with these equations when you can't actually see what's going on, when you can't observe it. And it kind of brings you to how small do things get. And it's quite interesting, right, that these Greek lads called Lepicus and Democritus came up with the idea first. They were like, hey, like all Greek philosophers said, they went, well, lad, Aristotle, we have a great idea that we came up with. And we think that if we keep chopping something up, we'll eventually get to the smallest amount of anything. And we can use that smallest subunit of anything to make all of the things that we see, from the clouds to the mountains and all that. And Aristotle slapped their hand and said, stop being stupid. So that idea died for about 3,000 or 4,000 years. And then in the Renaissance, people were like, maybe that's not that bad an idea. Maybe there is a smallest subunit of all matter, of all things, that you can use to build everything around us, right? And this was the reason this was contradictory was because we didn't have the idea that like energy or mass was conserved. You think that you would set a fire and all of the wood would vanish and it would vanish into the atmosphere and you've enjoyed your heat. And there wasn't any concept of conservation. But there was a scientist in the 18th century called Antoine Lavoisier. And what he did was he tested exactly that. He set a fire in a closed container and he burned material in it and then measured the weight of it before and after. Really simple experiment. And he found that the weight didn't change. So even though we were visually looking at a loss of volume of mass, it didn't change. So there had to be some subunit that was just turning into a gas of some kind that wasn't totally lost. So something had to be conserved, right? And so people started going, hey, maybe there are these fundamental subunits. And that kind of leads us into the late 1800s, early 1900s work where we started to look at the discovery of the atoms by John Dalton. And I think, Aidan, it's your turn to talk some physics.
It's your turn, Aidan. Here's the stick. I hand it to you.
I hand it to you and I go back to my Baileys.
This guy, John Dalton, and several other people, I think the idea was that they thought that atoms were these kind of indivisible things. They were these kind of like really strong, tiny spheres, and they made up different elements, and that different elements on the periodic table were made up of their own atoms, you know. But then actually, you know, we know from looking at our physics and chemistry books that that's not the case. And actually, you know, there's this entire storyline of things that have happened, and buckle up, kids, because I'm about to tell you about every single bit.
All the kids have already left the podcast.
The kids are gone. Only the mums remain.
Only the people who actually understand physics left, and they're just here to have a drinking game about these two biologists making mistakes.
Last week Andrew insulted all of the mums away, so now it's just
no.
I guess there's only those that are in between kids and mums. Okay, welcome. Sit down. Have a sup of a can. That's what I'm about to do.
Oh my gosh! Oh, we need it. This is a doozy.
So after Dalton, okay, and his idea of this solid atom, you know, other researchers during the time, and this is just before the turn of the 1900s, the 20th century, and this guy J.J. Thomson, you know, he actually had the earliest version of what is known as a particle accelerator. And all it actually was this, it kind of looked like just a little glass sphere. It was connected to a glass tube, and then there was another glass sphere on the other side. And you would heat up one side, and you would have a gas, like a helium gas in there. Okay. And it would excite the helium gas. It would send it through, and actually in that glass tube there were some electrodes, and it would actually it would basically yeet those helium atoms at the other side of the receiving end. And actually, he built this thing that was able to basically change the trajectory of the particles. And at the top of the trajectory were these tiny little light particles, and they were smaller than what they thought the mass of the atom was. In fact, they were really small. And J.J. Thomson found that they had this negative charge. And turns out that in 1897 he found the electron. And so it was actually one of his students then, a guy called Ernest Rutherford, about 10 or 20 years later, I think it was 1911, that he found the other two parts of the atom. So what he did, actually, he used radioactivity to, and the weird thing about radioactivity, we actually talked about it in one of our previous episodes, that radioactive elements actually give off these alpha particles. They just like decay, and they come firing out of the of these elements, and they come firing out like little bullets. Okay.
Yep.
And so if you actually point them at a certain thing, you can literally use them as these charged bullet particles, right? So what they did was, Rutherford and his students, they got these alpha particles and they started yeeting them at gold foil. Okay.
Yeah.
Gold is a really stable element. Okay, chemically, it's very stable. and so it won't. It's not very easy to knock its protons and neutrons, which are inside of its nucleus, out. And so actually they shot these alpha particles through this gold foil, and most of them went through. And they were like, great, okay, we understand. And then 1/8,000th of them didn't. And then they were like, so is it that the middle of these atoms are really dense? And actually they kind of calculated that it is this, the nucleus is this 8,000th of the size of an atom that's this really dense part, and it's filled with these neutral particles called neutrons and positive particles called protons. And so that's how the whole idea of the atom was basically devised.
Come up with,
And so, but you know, a lot of this sort of physics kind of went stale after that, and moving on into the 20s, 30s, 40s, actually some physicists started looking up at the sky and were like, maybe if we try and detect particles coming down from space, that we might be able to see something. And what happens is that you start getting these things called cosmic rays. So these weird particles start getting detected. And it's really weird because they use these things called... later they use these things called cloud chamber experiments, and it's when you go super high in the atmosphere and then you have this particle detector that actually detects these subatomic particles that are not electrons, neutrons, or protons.
No, that's cool.
And they come flying in, and before they get burnt up by the atmosphere, or before they interact with the Earth's atmosphere, they get detected. And actually, what they decided to do then was create these more sophisticated particle accelerators. What I was talking about that J.J. Thomson did, but instead they started smashing protons together. And what that does is it creates a bunch of different particles. And actually, throughout the kind of 30s, 40s, and 50s, loads of different theorists and particle physicists start finding these crazy subatomic particles, and you start finding things like pions, sigmas, lambdas, deltas. You get particles and antiparticles. There's loads of this crazy stuff going on, and actually there's this one guy called John Bell, and he's actually an Irish guy, and Andrew actually told me about this dude, but absolutely amazing. I didn't realise that we were represented in this story of things, but this guy John Bell actually found the pion, and he actually he went on to do some great stuff that Andrew will talk about later about quantum theory, but that whole field he added to that, but not to get into that yet, this kind of mountain of particles and crazy things that basically at this point in time, just after World War II, physicists were kind of like, this is chaos, this is chaotic, and they didn't really know what to do. But then in the 1960s, a guy called Murray Gell-Mann was looking at these kind of this zoo of particles, and he decided, this kind of makes sense, and there are symmetries in some of these particles. And he actually predicted that some of the most basic particles that we know, like electrons, neutrons, protons, they're all made up of things called quarks. Well, at least protons and neutrons are. And so he predicted these in the 60s. And actually, the funny thing was that after he predicted these things called quarks, which are actually like the building blocks of these subatomic particles, much like the periodic table of elements is to chemicals and to molecules. So these quarks were actually accidentally discovered. In Stanford, they were trying to take a electron micrograph, which is basically they were trying to take a picture of a proton,
right?
And in order to take an electron micrograph, you need to absolutely again yeet a bunch of electrons at a proton. And what they actually didn't realize was that would completely and utterly destroy the proton, or not destroy, but change the proton and cause a collision. And the collision actually caused them to find these signatures of quarks.
Mm-hmm.
And so that's
really
how the quark was found. So if you can think about it, like the perfect analogy is the kind of periodic table of elements, and that quarks are part of this kind of second level of table of subatomic particles. And actually, this brings us to what is known, and you know, over the next kind of 40 years, right up to modern day, and we get what is known as the standard model of particle physics. And so the standard model, now we know that there's actually 12 different subatomic particles. Okay, very confusing. Don't worry about it too much. But there's basically there's way less particles than there are like atomic elements. Like in terms of you know, there's loads of different atomic elements in the periodic table. There's a couple hundred.
Yeah.
Or no, there's like 150, something like that. And so there's only 12 of these that are matter. 12 of these subatomic particles. And to be honest, the only ones you need to worry about, and the only ones that we're made up of, are these things called up and down quarks and electrons. And then there's this fourth level called electron neutrinos, and they're totally weird. They're going through us all the time.
Oh, fun.
Actually, they're produced by the sun, and I don't know what the hell they do. I'm a biologist. How the hell should I know?
I was kind of waiting for like a... And this is what's... Okay, fair enough. You know what? Yeah, that is totally understandable.
But these... So, if you can imagine that there's one column with these four things, right?
Yeah.
And then go over, there's two families that are heavier, each one heavier than the other, okay? Mm-hmm. So, you have an electron, a slightly heavier electron, which is negative, is called a muon. And then the slightly more negative is called the tau, right? Okay. But anyway, imagine that for every single one, for the up-down electron, all those lovely guys. Right?
They all have some brothers and sisters.
Exactly. But the weird thing about those other ones is that they're slightly heavier, and they actually never exist for very long. So, like, electrons and up and down quarks, they exist as protons and neutrons and electrons in atoms. But these other things are kind of like intermediary... or maybe like, you know, they're in the middle of a process. You know what I mean? They don't really exist for very long, and they're kind of part of these different links to the creation of other things.
That's very confusing.
Very confusing. And to make you even more confused...
hit me.
Okay? There's four more of these particles, okay? But they're actually called bosons, okay? And they're
You're a boson.
You're a boson.
You're a
Don't you call me a boson?
Don't call me a boson either. Anyway, there are apparently four of them. Go on.
The idea is that those first 12 things that I was talking about are all called matter particles, okay? And basically they're called fermions. Your man, again, Enrico Fermi, going back to him. Enrico Fermi, fist pump.
That guy touches everything. Like, you'd swear this podcast was dedicated to the man. He's everywhere.
The Fermi podcast.
He is the Fermi podcast. Seriously though, like, shout out to that dude. He's everywhere.
He's everywhere.
Oh man.
Nuclear physics, astrobiology, amazing.
Yeah.
So yeah, let's confuse everyone more. Bosons are the opposite of the fermions. They don't hold matter. They are force carriers, okay?
Mm-hmm.
So you have this thing called a gluon. You have this thing that you know very well called a photon. And that is, you know, that's what travels at the speed of light. And so does a gluon. These other two dudes called Z and W bosons. But the idea is, and this is where we get into kind of quantum theory and there's these things called fundamental forces. Okay? Mm-hmm. And everyone knows what most of these fundamental forces are, or at least you know one really well. Okay.
Yeah.
You know this one called electromagnetic force. You know the electromagnetic force. photons travel through this and they interact with this force. Okay?
Do I know the electromagnetic force? That's a big. That's a.
You should.
Do I?
You should.
Any examples? Because I'm a.
Well, the idea that electricity can be turned into light. A light bulb is a perfect example of the electromagnetic force. You can use really powerful magnets to make things go really fast. You can
magnets, electricity. This is all kind of. They're all one family. Da 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 da. Yeah, I like it. Okay, so all these things are they're of the one family of the electromagnetic force. That's fun.
Yeah, so you got this electromagnetic force, and then you have a load of forces that you will have no idea about. No, the only other one that you will understand, and actually isn't included in this whole standard model, and it's something that we might talk about later because it's such a hard force to understand, is actually gravity. And so
Newton would disagree, but go on.
Newton's got a very easy understanding of this, but basically what not to talk about the force of gravity because it's actually not included in this standard model.
Wowzers.
But there's basically, for instance, that other thing that I talked about, the gluon, that is part of another force called the strong force or the strong nuclear force. What it does is it interacts with this force and it keeps quarks together. Okay?
Okay.
Quarks don't like to be alone. Okay, everybody needs a friend, okay?
Oh.
Bob Ross says it all the time when he's painting his beautiful little paintings, okay? Everybody needs a friend, okay?
So this is like the attraction between two lonely, teeny tiny particles.
Exactly.
We're going to have
Cork.
to keep... Yeah.
Up cork sees down cork.
Oh, bless. We're going to have to keep humanizing things because that's the only way biologists can understand this. So they like each other. Okay, I get that. I understand. They like it. Okay.
Biologists' take on particle physics.
They like each other and it's a force in nature. What can you do?
Strong nuclear force is basically like love.
Oh. And
so going back to reality...
Any physicist listening just went, they just shudder to their core listening to that.
Exactly. So, what are the other forces? The weak nuclear force. It's kind of...
Okay, it's more like a fling.
Yeah, it's it's basically a fling. It's self-explained. It's slightly weaker than... This strong force is so strong that you physically, it's almost impossible... You can't break these two quarks together. In fact, when you try and do it, what happens is that you actually create more quarks.
What?
When you put in enough energy, it actually creates another two quarks. So it's just like if you try and break two quarks, it'll break them into two quarks and two quarks.
I don't understand.
It makes my head hurt.
So these quarks are like super, super connected, right? And then you try to pull them apart, and
exactly,
it's like two people on a relationship going on break, and two other random quarks just they're like, hey,
just come in and it's like, whoop,
you're Uber compatible. Let's hop on in there.
And that, kids, is how toxic relationships are born.
Oh dear. Oh yeah, kids.
This is such a fruitful analogy.
I think
so.
It is.
Let's quickly move away from fundamental forces. Last one, weak nuclear force, is it explains radioactivity and how radioactive decay happens. Okay.
Okay.
It also explains how the sun works and how fission works and how nuclear fission and nuclear fusion works. So it's very important because it basically means that we can get a tan. Okay.
That's it.
That's all I have to say about that.
Okay, we went real in deep there.
No, okay, but there's one more thing about these forces, okay? And
okay.
This is maybe one of the coolest things and one of the most abstract things, and something that that Andrew's going to talk about more.
Oh yes.
In terms of quantum mechanics, but while all this crazy particle stuff is going on, it's great. People are finding particles left, right, and centre. They know what the hell's going on. They come up with this thing called a standard model, but this guy called, correct me if I'm wrong, Andrew, Richard Feynman, one of the kind of most famous quantum physicists, or just physicists in general.
Oh,
he's done a lot of stuff.
Lecturers, the whole shebang. He's a very interesting character. He used to go to his, like, the only things he'd bring to a conference were whatever he needed to present and a set of bongos. And he was something else, and he won the Nobel Prize. And on the day he won the Nobel Prize, he just went, I can today say that nobody alive understands quantum mechanics, after winning the Nobel Prize in quantum mechanics.
And after that, Andrew's going to try and make you understand.
Oh, I got this. Don't worry. Richard Feynman, who? Let's go.
So the only thing that I'll say about Feynman and his work is that this is a tough one to take in right now, everyone. But there's this very, very well accepted theory called quantum field theory. And it's that all of these forces and all particles exist and interact with a certain quantum field. So, take the photon, light particle. It interacts with the electromagnetic field. Take the gluon. It interacts with the strong nuclear force field. Z bosons, W bosons, they interact with the weak nuclear force field, and etc. And actually, for every particle, it has its own field that it interacts with. Okay? So easy peasy, am I right?
Sure.
And, you know, so this idea comes up, and it actually makes quite a lot of sense. Okay? And the reason it makes sense is because it goes back to the 1960s when this mathematician and kind of theoretical physicist called Peter Higgs. Oh my God, Andrew's drinking straight out of the bottle. He can't handle this physics.
I'm breaking here. I'm breaking.
It's rotting his little biological love brain.
Oh, I don't understand how am I meant to make a lovely analogy about this.
Why do all the particles not just love each other?
Isn't that the whole point? Go on, Aiden. I'll suck it up.
So this guy Peter Higgs in the 1960s, again going back, he actually predicts this additional quantum field called the Higgs field. Okay. Aptly named. And the idea is that it actually gives these two of the force carriers, the weak force carriers, mass. And what it actually really does, though, why we care about it, is that it actually unifies the electromagnetic and weak force fields, and it actually means that they're all just one, and it's called the electroweak force. Okay, just think about it like this: you have these several different forces and you have these different fields. Wouldn't it make a lot of sense, and wouldn't it be quite nice if you could unify them all and have this beautiful unifying theory?
Sure, that sounds great. Don't ask me to understand it, but yeah, sure.
If everything's unified, then you finally figure it all out. Okay? Because right now, I mean, I tried to explain that whole standard model, and it's all over the place. There's a lot of stuff going on. And it makes a biologist shit his pants. So, to find out if this Higgs field exists, what Peter Higgs finally came up with was that he told experimental physicists that you could actually identify a particle that would exist on this field called a Higgs particle. Okay. And that's, maybe you've heard of this Higgs particle because it's also termed the God particle, and the only reason it is because the fact that it would bring all this stuff and unify all of these theories together, this electroweak force and all of it would basically mean that there's a final force carrier, a final boson on that standard model that would kind of make a lot more stuff make sense.
That would help.
It would help. It would help a lot. It would mean that a lot of this stuff is actually quite unified.
Yeah, well, you know, like you were saying before with the quantum field theory, it's like, oh, look at all this cool information, but you know, let's completely ignore gravity. The one of the few things we can objectively, as anybody can see, that when they trip, they fall. You know, it doesn't take like they say, it's not the fall that kills you, it's the landing. It's, it doesn't take a physicist to figure that out.
No, so, actually, That's coming from two biologists, physicists. You guys are dumbasses. Gravity. Okay?
That's the one thing we got.
Love matters.
And just continue. We're not winning any favorites here.
So everyone between the age of children and mums, here's the cool part. This Higgs boson is what it's called. This particle, this God particle that people were saying. Physicists got together from around the world, and over about 30 or 40 years built this huge particle accelerator called the Large Hadron Collider in Switzerland. Okay, and it took decades, right? And this thing is 27 kilometers long. Okay,
that's excessive.
It's huge. So it's like a 27 kilometer not diameter, but it's 27 kilometers in length, and it pretty much covers the entire city of Geneva. All right, it's huge.
Wow, it's all underground, isn't it?
It's underground. It's about 100 meters underground, right? So what they do is there's these 4 parts of the ring that have these sophisticated detectors. The detectors are 5 stories high. If you see a picture of one of these things, and I'm sure unless you've been sleeping under a rock for the past 20 years, you will have known that I think it was in 2009 that I was in school, and I knew I was in secondary school, and I knew that the world was about the end. There was this whole idea that once they started this Large Hadron Collider, that would cause a black hole.
Yes, and destroy the known universe.
and at least sucking Earth into a black hole. But, the truth is that it does create a very, very small black hole. But it makes a black hole that is instantaneous and actually dissolves straight away. So the physics, like Stephen Hawking made that theory of the theory of black holes, and it was perfectly detected in those experiments. And so from about 2009 to 2012, they would send clusters of about 1 billion protons, and then they would send 1 billion protons in these little clusters the other way. Mm-hmm. And at these 4 regions, they would make them collide. And the explosion would create really high energy particles like the Higgs particle. That the Higgs particle doesn't really exist on its own at normal kind of stable low energy like as we are today, but during the very early startings of the Big Bang and just after the Big Bang, the Higgs particle would have been in existence if it was correct, if that theory existed.
That's crazy.
It's amazing. So, dude, the analogy that I have for the Large Hadron Collider and colliding these billion protons against these other billion protons is that you get maybe 10 of those protons collide, right? And it's like getting 2 really crappy cars and smashing them together and then creating a beautiful Ferrari that then vanishes like out of thin air. You just like clash them together and it's like, oh my god, poof, and then it's gone. And that's what happens, right? And actually, the thing is that they detected the Higgs particle. They did this, and they found it at it's something like 125 times the size of a proton. And but the thing is that they detected this, and the way they detected it is from what it decayed into, and then the things that it decayed into hit the sides of the detector. So it's amazing. It's absolutely incredible, the sort of things and calculations and detections that they can do.
I don't understand anything of what you just said. So wait. So this was 125 times the size of a proton.
Yeah.
And it you smushed these together and you magically developed this Ferrari Higgs boson God particle, which then crumbled into, once again, your crappy 2 cars that were, or crap, let's say the God particle was the engine, and then it just crumbled back into these components of the engine. Is that it? And they were like, oh, well, you could only get the God particle from these components of the engine. It's nearly
similar. So you're getting these 2 kind of crappy cars that are fully you're getting two full crappy cars, and you're eating them at like it's 99.999999% the speed of light.
Okay, a little quick, but go on.
6 nines. You're hitting these two cars together. It creates, for the slightest instant, the Ferrari, the God particle. Then those decay into two different crappy cars. And what's detected are the two different crappy cars. Okay. And you can go back, you can basically back calculate, well, what was the mass of the thing that those two things decayed into?
Okay.
That's how they do it.
That's crazy.
And what's amazing is that they take, it's something like 16 million detections a second. So that it's like a huge camera. And the camera is like, it makes a beautiful 3D image of what just happened. And actually, there's so much data that it only saves the interactions that kind of maybe are in the lines of a size that would be important to them. So I heard some people saying that, look, if you actually logged every single one of these collisions, because they do them all the time now, that it would literally fill up every single hard drive in the world. It would just, no one would have space in their computer if you
well, like that totally makes sense, because you'd be taking in information from literally all of existence.
Yeah.
You know what I mean? Like that is like it's completely nuts the way that they detect these things. Like even just taking a picture of an atom is nuts. The idea of just smashing
these little
smaller
tiny
particle, and then like what one in 8,000 gets into a fender bender. It goes off at an angle, and you're like, oh, I wonder what that hit.
It's more like 10 and 2 billion.
Yeah. No, but I meant with the gold and the beta decay that you mentioned before.
The nucleus, yeah.
Yeah, but it's a similar concept for detecting these, because it needs to. You're not detecting the thing itself. You're detecting the things that boink off of it. You know, and that's
how the quark was found as well. You've never actually found a quark. You've seen the deflections off of a quark.
Oh, but Aidan, you are the quark. I'm just trying to scare off the physicists, you know.
And they're like, oh, that's it, I'm done.
Yeah, that was it. That was the line. I can't do it anymore.
So, I don't know. Let's just reiterate. CERN and the Large Hadron Collider, they did it. They found this thing. And
it's amazing.
The significance is that, yes, it confirms that there might and very may well be this Higgs field. This, in other words, this electroweak field. And it unifies those forces. And the idea is that at even higher energies, that you might be able to create particles that might also unify the strong nuclear force. So this whole theory, and it's an amazing theory, it kind of pushes into this last thing that I want to talk about, that's known as supersymmetry. And it's an idea that, so I only mentioned it really briefly, but during that zoo of particles that were being found in the kind of 1940s and 50s, there were antiparticles as well. So there were particles and there were antiparticles. It's like you get an electron and it has a complete opposite charge, and it's called a positron. Okay? You get an up quark and you get an anti-up quark. Okay? They are physically, they exist. Okay? So, and we have detected those. Those were actually detected. Some of them were detected before they were even predicted. Okay?
Okay, cool.
There's this idea that there's actually even another set of the standard model called superparticles or sparticles, which sounds super cute.
Sparkicles.
So like your quarks are your squarks, and your, I don't know, your electron is your selectron, and your, so your muon is your smuon, all of that stuff.
Oh, a smuon.
It's cute.
Oh,
okay? But this idea is that you have the standard model and your electron is negative. You have the antimatter where your electron is positive, and then you have this other standard model in the middle that's neutral, and it balances them out. Okay?
Yeah.
Maybe that makes sense.
To who?
Yeah, not to me. And so the overlying idea is that all of those matter particles that I was telling you about, those fermions, they all have a opposite force particle. And all of the 4 force particles that I was talking about in the general standard model, gluons, photons, Z, and W plus minus bosons, they all have opposite matter fermion particles. Okay?
Okay.
It all balances each other out, all right?
Mm-hmm. It's all conserved.
And actually what this would do, and this, once you do the calculations, like me and Andrew know what the hell that means, it brings the Higgs field to an equivalent strength that allows matter to exist in the way it exists in our universe. Okay?
That sounds useful.
It's very useful because when us biologists do the math, the incredibly complicated math of that sort of calculation, what you find is that it's really kind of lucky. Like, we're really lucky that we have this Higgs field that exists at this certain size so that everything else can exist, and that matter and quarks can make up protons and neutrons and electrons, and that they can create atoms, and that atoms can create matter or larger compounds and molecules and life. So it seems to add up way too nicely. But actually, so this supersymmetry would make a lot more sense in that those sparticles are the reason why this Higgs field is at the level that it's at. That it's not giving way more mass to certain particles that or making certain particles massless. Because if every particle was massless, everything would travel at the speed of light, like photons. Photons don't have mass. Gluons don't have mass. So they travel at the speed of light. Okay? Everything else doesn't, because Higgs particles interact with them and give them mass. And that's the whole idea.
Okay.
Super duper great. Last thing I want to talk about.
Hit me.
This would actually explain some stuff to do with dark matter and dark energy, because physicists actually know this already and have known for quite a while, that there's about the matter that we know, atomic matter, made of up, down quarks and electrons, everything we know, stars, everything. That's 5% of the matter in our universe. Okay? 95% of the other stuff in the universe, we don't really know what the hell it is. Okay? And physicists call it dark matter because they don't know exactly what it is.
Okay.
And it might make sense that this dark matter is actually the superpartners or the sparticles that I was talking about, those neutral particles, and it would make sense because they don't have a charge. And so they're just these kind of invisible neutral particles that don't really interact with our version of the universe and our matter that we are made of. Okay?
Yeah, I guess. Okay, yeah. Just nod along.
Great.
Yeah,
that's great. That makes
sure.
total sense.
I get you. I'm with you. Yeah, totally. Yeah.
And the last thing is that, and this is kind of amazing, it's that I don't fully understand this. I mean, I don't understand anything I'm talking about right now. But the idea is that based on the kind of first standard model that I was talking to you about, after the Big Bang, matter and antimatter should have met equivalently and annihilated each other. And so the universe should have just been full of photons fizzing around at the speed of light. Okay? But it's not. We're all having a great old dandy time on Mother Earth, and we're looking for other places to cause global warming. Okay?
Yeah, fun. Yeah. Love it.
And this supersymmetry idea again would add up to and explain why there is an imbalance of more matter than there is antimatter in the universe, and in fact it is about a billionth of the matter that was destroyed at that moment when all matter met antimatter. So everything in the known universe that is made up of this atomic matter that we're talking about was a billionth of what was at the start of the Big Bang. And with that, good luck. I'm just going to leave.
Is it mine? You're going to leave it at that? I have no idea what you just said.
Look, I'll leave.
Okay.
No, but I'll finish off this section with a quote from this guy called Harry Cliff. And maybe
go for it.
This might make a little bit more sense. Maybe it won't. But it's based on the same premise, okay? He says, you and I are leftovers. Every particle in our bodies is a survivor from an almighty shootout between matter and antimatter that happened after the Big Bang. In fact, only 1 in a billion particles created at the beginning of time still exists today. So that was part 1 of our journey through tiny physics. Go and listen to part 2, you absolute science-loving scallywag.